So water is something we take for granted. It's actually rather extraordinary. Water has a low molar mass, 18 grams per mole, but it's a liquid at room temperature. This is not typical. So here we have a little graph where we're looking at the boiling point of these substances. These are all H2 and an element, and these are group 6A on the periodic table. Oxygen is in period 2, sulfur is in period 3, selenium in period 4, tellurium in period 5. So tellurium is larger than selenium. Selenium is larger than sulfur. And so we see this linear trend here that the larger molecule has a higher boiling point. That's because the dispersion forces are stronger. So if we were to draw a line here, it's not exactly straight, that's the best I can do. You see this trend. The prediction here is that water would have a boiling point of about minus 100 degrees Celsius. If that were the case, water would be a gas at room temperature. There'd be no oceans, no rivers, no drinking water. All the water in your body would be a gas, not compatible with life, right? But it doesn't. It has a boiling point of plus 100 degrees because of hydrogen bonding. Water is a very small molecule. It's got the hydrogen-oxygen bond, and so it has very strong hydrogen bonding. That causes its boiling point to be much higher than predicted, and it's a good thing. It's also very polar, which means that it can dissolve lots of other polar compounds and ionic compounds. It's sometimes called the universal solvent. It's the predominant solvent of living organisms. And so the water in your blood is what is distributing minerals and things to your body. People are looking for life on other planets. And if there's no water, there's not going to be any life. So that's what they're looking for, is water. When water freezes, it's also unique. Most substances, when they freeze, shrink a little bit. They contract. Water expands when it freezes. And this happens because it forms an open crystalline structure to maximize the hydrogen bonding in the water molecules. And so that causes ice to be less dense than liquid water, which means that ice floats. We all know that ice floats. But in most substances, the solid would sink in the liquid. That also would change life on our planet. So I grew up in Minnesota. In the winter, the lakes freeze over. But the freezing starts at the top where the cold air is, and it forms a layer of ice. The ice gets thicker and thicker as the cold goes on. But instead of the ice forming at the surface and falling to the bottom, and more ice forming at the surface and falling to the bottom, which would result in the lake freezing solid, we just get a thick layer of ice on the top that acts as insulation and keeps the rest of the lake from freezing. If ice was more dense than water, there'd be no fishing in Minnesota. That'd be horrible. This has a big impact on what happens to living organisms when they freeze. So you think of lettuce, right? If lettuce gets too cold in your refrigerator and freezes, what happens to it? It gets all wilty and limp. I mean, you can thaw it out, but it's not going to be very good, right? Because when the water freezes, it expands and it breaks the cell walls. So all the cell walls in the frozen lettuce are broken, it loses its structure, and it just turns to mush. So high water content foods generally don't freeze very well. One way you can get around that is flash freezing. This can't be done at home, but industrial plants can do this. And what they do is they freeze the food so quickly that the water molecules cannot organize themselves into the crystalline structure, and so they don't expand. So by flash freezing, you can freeze certain vegetables and fruits without destroying them.